In the previous video, we talked about the Hill cipher's theory, so how it works and what you can expect from it. So it's now time to implement what we were talking about there. So let's start. So we're going to import numpy as np, and our m, as in the example which we used in the previous video, is 3. And the plain text which we used there as well was pay more money. Okay. Then we also had a key which was predefined. So let's just quickly define that here as well. So the key was 17, 17, 5 on the first row, then 21, 18, 21, 2, 2, and 19. If you want to add some space, feel free to do so. Something like that. Okay. Then moving on to the ciphertext, which is currently empty. It's an empty string. We haven't started the encryption process. And before we get to that, we want to make sure that this plain text is divisible by m. So that's the general case. In this case, it is, but we don't want to assume that our plain text will always be divisible by m. And it has to be divisible by m because we want m columns to be multiplied by this. Okay. So let's do that. Let's check for, so ensure plain text divisibility, something like that. You can name it something else, but that's what I'm going to call it. So we want to check if we have remainders when we divide the length of the plain text by m. So remainder will have a non-zero value if it is not divisible by that. In this case, the value will be 0. So if the value is not 0, or if our remainder is not 0, then we want to add some filler text to the plain text such that it becomes divisible. So we're going to use x as the filler text, as we said in the theory section, and we're just going to add a bunch of x's until our word is divisible by m. So it only makes sense that the remainder would be less than m. Otherwise, it wouldn't make sense for that to be a remainder. So imagine 4 divided by 3. The remainder there is 1. 5 divided by 3, the remainder there is 2. 6 divided by 3, the remainder is 0. So the remainder will always either be 1 or 2, or it will always be less than m. So the number of x's that we need to add are m minus the remainder. So if the remainder is 1, we have to add 2 x's. In the case of 4, then that would be 3 minus 1, which would be 2. So we need to add 2 x's so that the total count is 4 plus 2, which is 6, and 6 is divisible. So that's how this works. That's how I figured this out. So that's how you make sure that the plain text has letters or a total number of letters that are divisible by m, whatever m is in your case. Moving on to the encryption process. So NumPy really helps in this case. So you don't really have to do much, but I just want to use the same approach which I used in the theory section, because there we dealt with each row. So we dealt with one row at a time. Well, mathematically, you don't have to, because matrix multiplication does that for you. I guess you can do that as a homework assignment. So instead of going through this for loop like we're going to do now, just multiply P and K modulo 26 and you should be good. Right, but let's go through this using the approach that I covered in the theory section. So we're taking m at a time. So in other words, or in this case specifically, we're taking 3 letters at a time. So that's how this works. So our for loop will go through each of the letters and it will skip m to go to the next m. So it'll start with pay, then skip those to go to the next 3, then the next 3, and so on. And as we've figured out, these have to be changed to numbers. and we're going to do that in here. Okay, so from 0 to the length of our plain text, skipping m, we are going to take a piece out of our plain text. So we're going to call this plain text piece, and that piece would be the plain text from wherever we are to I plus m. So the last one here is excluded. So if we have plain text, so let's start here at the beginning with, so this should be I in range. So let's start here in the beginning with an I of 0. This is what this would look like. It would be, the piece would be plain text 0 to 0 plus 3, which is 3. So now we'd only take 0, 1, and 2, and 3 is excluded, as I said. So I plus m is excluded. So indices 0, 1, 2 are PAY, and that's exactly what we expect to have. So this is not inclusive, at least in the closing part, the last part of it. So it's not inclusive. That's how you take 3, then you're going to move on to the next 3, and so on. So the next one will be 3, and then 6, and that's how it comes. The first one, we've already used that. We've already used the first one as an example, and that's how you pick your pieces of 3 or m. Okay, so we don't want to have a 3 there, even though we know that m is 3, so that you can use the same code for different values of m. Then we want to convert those letters into numbers in the range 0 to 25 inclusive. And this is how I'd go about doing that. I did a bit of, I combined these two things. If it's easier for you, we can split this. Let me think about it. Let's just combine it anyway. So we have a row of numbers, and we're going to print the row just so we are sure of what we're doing here. And this row has each letter converted into a number minus 97. So remember that A is 97. So if each of them subtract 97, then we are scaling the numbers the ASCII numbers 97 and up to 0 and 25. So without this minus 97, this function will return 97, which is the ASCII value of small letter a. But we ultimately want our numbers to be between 0 and 25. So how do you turn 97 into 0? Because that's the start of our count. You subtract 97. And any other ASCII value that comes after it should also subtract 97 to use it as a reference or starting point, so that we have 0, 1, 2, and so on. So that's the first part. So we're going to convert each letter to its ASCII value, then subtract 97. And this is for each letter that's in the piece that we just took. So this is a piece that we just took. So not any other place. So we have a piece from the plain text, for example, pay. And for each letter there, we're going to calculate the ASCII value minus 97. And that will be contained in a list. We then convert that list into a NumPy array. And that's what this line does. And that is our P, which we're dealing with at this time. Then after that, to form our ciphertext, we are going to perform the dot product of that P that just has 3 numbers multiplied by the key. This is how we did it in the theory section as well, modulo 26. And that is literally it as far as the calculations are concerned. So we also have to convert these numbers back to some ciphertext for us to see and confirm. And to do that, we're going to have a ciphertext piece, which is not the whole thing. It's just this piece. So the cipher of this piece that we're currently dealing with. And that would require us to convert the number back to characters and use this inbuilt function, chr, for character. And we're going to have I plus 97. So whatever number is in C, which we just calculated here, for I in C, whatever number is contained in there would be converted into a character plus 97. So remember that we converted these to 0 from 0 to 25, and we have to take them back to ASCII numbers so that CHR can recognize what they are. If you just pass in 0 to 25, this will produce something which is totally different. So we have to use these scaled values that we get there and add 97 to each one of them so that this contains values that are recognized by the ASCII table. Okay, then from there, we are going to use a join to convert those ASCII numbers back to letters. So here, in this case, they are characters actually. So the conversion happens in here, but this is still a list. So to convert a list into a string, we can use this join function. So an empty string not joined to a list will convert that into a string. So this part only converts these ASCII numbers into a string. So that's all that it does. So as I said, let's confirm these parts as we go along just to see what's going on and to compare it with our theory section. So this is, we can call this the plain text piece, and it would be exactly that. Then here we can have, let's just focus on in the theory section, we also had the Cipher modulo 26, so we can have that as well. Just so you compare this with what you got there. So Cipher text piece, and then we have the Cipher text piece as well. And finally, we have the Cipher text piece, which is represented by letters. So ciphertext piece letters, something like that. And we'd have in here, we'd actually have the ciphertext as it is at that moment. That'll be, okay, so it'd be this joined with, would have to do this again to only have a piece. So that would require us to just have this in here and not the whole thing. Otherwise, we just incrementally add to it. Then after all of this, we expect to have the final ciphertext, which we also had in the theory section. And that would be ciphertext. Okay, so here we're just printing what we have at each stage. So you're going to deal with pay first, then, but here we're going to see it in its number form between 0 and 25. Then we're going to see what the ciphertext piece is and compare that to a theory section. Then here we're going to have our ciphertext piece letters that we're going to get from the plaintext and the key. Then finally, we're going to have the whole ciphertext done here. So let me run this just to see what we get. And it appears we have an error. It says ciphertext piece is not defined. So where is that? Ciphertext piece is defined there. Did I misspell this? Maybe. Line 23. So at line 23, it's not defined there, which makes sense. So I tried to call it, I tried to use it before its definition. So let's put it after that, and we should be good to go. So let's rerun this, and these are our results. So at the first run of the for loop, we're going to take pay, and pay is now converted into RRL, and then in text form, that's RRL there. So let me see if you can't get the numbers out of this. So that would be C instead. So let's print C, or let's use P there, and then use C there, because these are the numbers that we used as well in the theory section, we only focus on these numbers. So 15, 0, 24, 17, 17, 11. That looks familiar to me. I hope it does to you as well. Then the ciphertext that we get out of that, or this, is converted into RRL. Then we have 12, 14, 17, that, and then we get MWB. That also looks familiar to me. Then we have 4, 12, 14, 10, 0, 18, KAS, and then this, which finally gives us PDH. Then when we combine each of these, we now have RRL, MWB, KAS, PDH, which is exactly what we got in the theory section. So this is encryption using the whole cipher. And as I said, you don't have to use a for loop. You can just directly convert this whole thing into a matrix, then have the dot product of that directly with the key, then convert it into text like I did down here. That should still give you the same thing. Instead of taking M at a time, you don't have to do that. Okay, so let me remove all of these print statements and let's move on to decryption, which is a bit different. So we now have encryption up here and we can move on to decryption. Let's get that maybe down here. Decryption. And here we are also going to take M at a time just to be consistent with the encryption. And I have to mention that the inverse here, so if you've done a linear algebra course, you probably know what the inverse is. So the inverse here isn't directly translatable to what we're dealing with here. Here, we're dealing with the inverse modulo something, and it's different from your normal inverse. It has the inverse of the determinant of the key multiplied by the adjoint matrix, and yeah. So we'll look at all of that jazz now, and you'll see how it's different. And in there, your normal inverse is also involved. So this is decryption. And the first part of this, we can just use a different variable so that we don't mix the ones that we already have up there. So we can just call this decrypted plaintext so that we don't use the same plaintext variable because it might be unchanged and we can claim that we've done the decryption even though we have not. So decrypted plaintext, then let's find the inverse of K because that's what we're going to use the most. Well, this is the most important part of the algorithm. So we're going to find the determinant of K determinant, that's what I'm going to call it. And we want to make sure that it is rounded. So that's why I have that there. And I'm going to find the determinant using this numpy function. So that gives us the determinant of K. Then we want the inverse of this determinant, which is quite interesting. So if you try to do this as you know it, as in 1 over this determinant modulo 26, then modulo 26 again, it doesn't work out because there's a lot that happens in the background that has to do with Fermat's theory or something like that. Okay, so this is how you'd go about it. Using the power function ensures that you have the correct calculations. So this modulo 26, then this to the power -1, then modulo 26 again. But if you try to do it manually, you get a totally different answer. So just watch out for that. Then we want to find the aggregate matrix of K, and that would be, once again, let's round to ensure that we don't have any floating point values. And we're going to calculate the inverse. So this is the inverse that you probably know of K, then multiplied by the determinant. That gives us the aggregate matrix. Then we can finally have the inverse. And if you want to define it in full, I guess you can. Modular because it's important to differentiate this. That name's too long, but at least it helps us to understand what we are doing. Okay, then this would be our determinant inverse multiplied by the adjugates. Once again, modulo 26. We now have K inverse after all of that, which is a bit crazy to me, but this is just what we have to do. So for I in range, so now we're doing the decryption, we're going to take M at a time from the ciphertext. So we already have the ciphertext. So after this, remember that we have the ciphertext in full, which is RRL, MWB, and so on. So you're going to use that because we want to use that to get this back. Expect to get that back. So if you encrypt something, expect to get the plain text back as we had it. So now we have for I in range that from 0 to ciphertext length, skipping M at a time or taking M at a time. Once again, we're going to define ciphertext piece, and this doesn't affect this one there because they're in two different scopes. So once you start the for loop, this is a different scope and it doesn't have access to that other one. And then we're going to take a piece of the ciphertext like this. And then we're going to remember that for decryption, we have P equals to C multiplied by K inverse. So now we have C, which is the piece that we now took here. And this piece will be converted into numbers from 0 to 25, just as we did with the plain text. So that's what we're doing here. So odd or RD of the letter minus 97, also have to do that here as well for letter in the ciphertext piece that we just took. So our RRL, for example, we have to convert all of that into numbers in the range 0 to 25. And after that, we can do our calculation. And our calculation just involves us doing the dot product of that plain text piece multiplied by or dotted with the K inverse, which we just used there. So that long thing that we have there. Let me just take this part to replace that. And then once again, modulo 26. Then the piece that we get out of that will be a plain text piece. And we need to convert that into letters again. So we're going to now take whatever we get from there. Do I need to round this? Let me think about it. Just to be safe, let me just keep it there. And then it'll be whatever value that I got between 0 and 25 added to 97, going into the char function for I in P, which is the plain text which we would have got from decryption. Then once again, we're going to add each piece of our decryption to the total, which is stored in there. So decrypted plain text, that's what we called it. Plain text plus equal to this list converted into a string. So that's what we're going to have there. So that would be plain text piece, right? Then we can have our final print statement. I don't think it's necessary to go through each one unless if we run into a problem or we don't get the plain text back, then I guess we can go back to this. So we can call this decrypted plain text, and then we can put that in brackets like that, then close this. So let's see what we get from this. I'm just going to run the script, and it says decrypted plain text, pay more money, which is exactly what we expected. So this is how you implement the Hill cipher in Python. We went through the encryption as well as the decryption. So if you have any questions, leave them in the comment section, and any other thing as well that you want to say, leave that in the comment section, and I'll see you in another video. For now, comment, subscribe, and we'll discuss yet another algorithm in the next video.